So, hi, this presentation will discuss how to combine light from multiple light sources in the Phong lighting computation. The basic principle is just that we add up the light from each of the light sources and make that the final light assigned, or the final brightness assigned to a point on the surface. But we do want to be a little careful with this. So first of all, we assume we have lights L1 through LK that are currently turned on or enabled. If any lights are disabled, we'll just ignore them from the computation and only work with the ones that are turned on. The ith light has intensities, incoming light intensities, I in IA, the ambient incoming light, I in ID, the diffuse incoming light, and I in IS, the specular incoming light. The extra superscript I indicates that it's coming from the ith light. Now we could actually also add extra superscripts for the color, red, green, or blue, because we're going to redo this computation for each of the wavelengths of light that we're working with, usually red, green, and blue. But the formula I'll just treat for one wavelength and let you generalize it to all wavelengths. The one thing to watch out for is that some lights will be below the surface. We have multiple lights turned on, not all of them are going to be shining on the surface. So we'll set I in ID and also I in IS equal to 0 if the ith light is below the surface of the point we're illuminating. So our situation is the following. I've got some surface, some object with a point X on it. X has a normal vector, of course. It's got a view vector. It's got a plane tangent to the surface here. And the lights, some lights could sit up here, but other lights could sit below the surface. So lights that sit below the plane tangent to the surface obviously are not shining on the point X. And for those lights, we'll use the formulas with ID and IS set equal to 0 because this light below the surface doesn't have any diffuse or specular contribution to the illumination of the point X as seen by V. It does, however, have an ambient contribution because the ambient light is something that we think coming out of this light and then spreading generally around the whole scene. We let delta I and delta I prime be the distance attenuation and spotlight attenuation for the ith light. Okay, and finally we have one more value here. We'll have an ambient global light, I global A. So this is global ambient light. Which is intended to be light that's turned on all the time, even if none of the lights are enabled. Since we generally allow lights to be separately enabled and disabled, it's nice to have an ambient light that just is always present. And we're now going to use these values to give the sort of master Phong lighting equation that gives the results of illumination from all these lights. Now I'll give the overall Phong lighting equation in the situation with multiple lights, including distance attenuation and spotlight attenuation. We'll express this in terms of its components IA, ID, IS, and IE. So IA will now equal to rho A, the ambient reflectivity coefficient, times the global ambient incoming light, plus, and we sum over all the light sources, I equals 1 to k, delta I times rho A times I in IA. So we take the distance attenuation of light I times the reflectivity coefficient for the surface times the incoming light for light I, incoming ambient light for light I, and we sum those up, and that gives us the overall ambient light component. ID will be the summation from I equals 1 to k of delta I prime. These are the distance attenuation and spotlight attenuation for the ith light, times rho d times Li dot n, the vector to the ith light, dot product with the normal vector, times I in ID. So we're just taking the diffuse component from each light source times the reflectivity coefficient for diffuse light times the appropriate attenuation factors. IS is similar. It'll be the summation of I equals 1 to k, delta I prime, rho s, Ri dot v, that's actually, we need the max with 0 part version of this, max of 0, and Ri dot v, that's the reflection vector dot product with the view vector raised to the specular exponent f. That's a material property. It's always fixed, does not depend on the light, times I in IS. Or we can use the halfway vector formulation. The summation from I equals 1 to k of delta I prime times rho s times hi, the halfway vector for the ith light, dot n, to the specular exponent f times I in is. So again, it's the same specular computations per light, now including the attenuation factors and summing them up. Alternately, you can use the Schlick approximation and for Fresnel lighting, and then we use rho Schlick I instead of rho s, because now we have a superscript I on the rho Schlick coefficient, because the Schlick coefficient depends on the angle theta that the light direction makes with the normal, and that depends on the light. So this gives you IA, ID, and IS. IE is just given as a material property, and we sum these up to get I is IA plus ID plus IS plus IE. In this version of the equation, I've incorporated the attenuation factors into the ambient, diffuse, and specular lights already. So this is the light as seen by the viewer in the setting of multiple lights. Two further comments. First of all, we do this separately for the red, green, and blue components. For different color components, usually red, green, and blue. So the typical thing is we have all these colors for red, all these, and material properties and light properties for red, all these materials and light properties for green, and similarly for blue. We do this computation separately, and then we add up each component by its own, and then combine it into the final color. The other comment is that the I values should be in the range 0 to 1. So they should be greater than or equal to 0 and less than or equal to 1. 0 represents the darkest color that can be represented or shown on the screen. 1 is the brightest color that can be shown on the screen. You want to have values between 0 and 1 because we want to have colors changing subtly across the surface to give the appearance of three-dimensional surface. And that's important. If we just saturate the colors by clamping everything at 1, it'll just, again, look like a flat, bright color without any appearance of three-dimensionality. In practice, this means that when you're adding up multiple lights, each light has to be not too bright, so that when you sum up the colors from all of the lights, you get values for red, green, and blue that are all less than or equal to 1. that's the end of this presentation. Thank you very much.